Hello friends, in this video I'd like to solve the following problem from the Thailand Mathematical Olympiad 2020. Problem number 1. We wish to show that phi of 2 times n divides n factorial for every positive integer n. What is phi of n? Well, it's the Euler's function, which is defined in the following way. Phi of n is the cardinality of a set of positive integers which are less than or equal n and which are co-prime to n. So in other words, we are taking integers from 1 up to n and we count how many are co-prime to n. And this it's very famous arithmetic function. This function has various useful properties, namely, for example, phi of p to the power of alpha equals p to the power alpha minus 1 times p minus 1 for every prime p and alpha, which is positive integer. Moreover, phi is a multiplicative function. What does it mean? It means that phi of m times n equals phi of m times phi of n if m and n are positive and co-prime integers. As a special case of the point given above, phi of 2 times n equals phi of n for every odd n. And my proper hints for this problem. First, consider cases where n equals 2 to the power of alpha and when n equals p to the some power of beta, where p is odd. Consider these special cases first, and then prove and use the following lemma. Namely, if we are dealing with k integers, positive integers, then the product of their factorials divides the factorial of their product. So give this problem a try and I will see you in a minute. Okay, so my proof. First of all, I will prove the lemma which I stated. Lemma says that if a1, a2, and a sub k, let's say, are positive integers, then a1 factorial, a2 factorial, and so on, ak factorial divides a1, a2, ak factorial. Well, I will prove it in the case of two numbers. Proof for k equals 2. I will leave the general proof to you. It's very easy, either by induction or by seeing what's happening. The only tricky case is k equals 2. So okay. So we now have two subcases. First, if a1 equals 1, then obviously a1 factorial times a2 factorial is just a2 factorial, and it's equal to a1 a2 factorial. So divisibility or even equality holds. If a2 equals 1, the same, we have equality. So now let's assume that we are dealing with numbers which are integers but greater than or equal to both of them. Notice the following. a1 factorial, a2 factorial divides a1 plus a2 factorial. How do I know that? Well, because a1 plus a2 choose a1, it's just a1 plus a2 factorial over a1 factorial, a2 factorial. And we know that this binomial coefficient has combinatorial meaning, and this is an integer. So the right-hand side is an integer as well. And moreover, a1 plus a2 is less than or equal a1 times a2. It's pretty easy to see that equality holds only in case of a1, a2 equals 2. In other cases, we have strict inequality. And that implies that a1 plus a2 factorial divides a1, a2 factorial. And now combining this and combining this, we now know that a1 factorial, a2 factorial divides a1, a2 factorial. The rest is left to the watcher. Use induction or something. It's not that hard. QED. QED for the lemma, not for the entire proof. Okay, so now let's go back to our problem. And I will consider 3 cases. Case number 1 will be n equals 2 to some power alpha, where alpha is a natural number. What happens then? Then, let's take a look. Phi of 2n is phi of 2 alpha plus 1, and that is, by one of the properties which I mentioned, it's just 2 to the power of alpha times 2 minus 1, which is 2 to the power of alpha. And let's also see that n factorial, it's just 1 times 2 times 3 times finally 2 to the power of alpha. And our divisibility, of course, is true. So we see that phi of 2 times n does divide n factorial. In this case. Case number 2. Case number 2. N equals p to some power of beta, where p is a prime greater than or equal 3. Beta is a positive integer. Why not 0? Because p to the power of 0 is 1, and the case of 1 was already covered as 2 to the power of 0. So we need not consider this case. And let's look what happens now. Phi of 2 times n is phi of 2p to the power of beta. And as I suggested, phi of 2 times some odd number is just the same as phi of p to the power of beta. Okay, and what's that? Well, it's p to the power of beta minus 1 times p minus 1. Very well. And what is n factorial? N factorial is 1 times 2 times 3, and so on. Along the way, we will encounter p minus 1, and finally, in the end, we will encounter p to the power of alpha, 2 to the power of beta. And now let's take a look. P minus 1 divides this occurrence of p minus 1. P to the power beta minus 1 divides p to the power of beta. Which means that also in this case, phi of 2n also divides n factorial. In this case. And now the general case. Case number 3. The general case. What can we do? So let's write, let n be equal 2 to the power of alpha, p1 to the power beta 1, p2 to the power beta 2, and so on. P, let's say k to the power beta k, where alpha is a natural number, p1, p2 up to pk are distinct odd primes, and moreover beta 1, beta 2, and so on, beta k are positive integers. We know that every number can be written uniquely in this way. Yes, it's just prime factorization theorem. Okay. And now, let's see. Phi of 2 times n. What is that? Phi of 2 times n is the same as phi of 2 to the power alpha plus 1, p1 beta 1, p2 beta 2, and so on, pk beta k. And now, using the fact that our function is multiplicative, it's the same as 2 phi of 2 to the power alpha 2 to the power alpha plus 1, phi of p1 beta 1, phi of p2 beta 2, and so on, phi of pk beta k. And now let's do the following. 2 to the power alpha plus 1 is 2 times 2 to the power of alpha. Phi of p1 to the power beta 1 is the same as phi of 2 p1 to the power beta 1. Why is that? Because this part is odd. It's one of the properties of phi function. Here as well. Okay, and now, using the cases 1 and 2, we know the following. This number divides 2 alpha factorial. This number divides p1 to the power beta 1 factorial. This number divides p2 beta 2 factorial. Finally, this number does divide pk to the power beta k factorial. Perfect. So we know that phi of 2 times n does divide 2 to the power alpha factorial, p1 beta 1 factorial, p2 beta 2 factorial, and so on, pk beta k factorial. And now, using our lemma, 2 to the power alpha factorial, p1 beta 1 factorial, p2 beta 2 factorial, and so on, pk beta k factorial. This number divides product of factorials, divides the factorial of a product. So this divides 2 to the power of alpha, beta 1, p1 to the power beta 1, p2 beta 2, and so on, pk beta k, everything factorial. But look closely. What is that? That is n factorial. So we know that this divisibility is true. We know that this divisibility is true as well. Combining these two facts, we now know that phi of 2n divides n factorial for every positive integer. And that was exactly our goal. QED, quod erat demonstrandum. Okay, so thank you for watching. I hope that you've learned something new. These types of problems, to be honest, they happen from time to time on various mathematical competitions. In my country, in Poland, to be honest, they do not appear almost at all, or they do not appear in the formulation of the problem. But in Thailand, as we see, because this was from Thailand, they happen from time to time, and I'm glad that I've managed to solve it. Thank you for watching, and I will see you soon. Goodbye.